So we're going to discuss proving causation. Now we kind of came across this idea when we were looking at this data set earlier, and that is how life expectancy has changed over time. And as we increase the slider and take a look at how life expectancy has changed, you know, one of the temptations is to say that, oh, as time increases, life expectancy increases. But we know that's not true. So how do you establish a cause and effect relationship? What is it that finally says, okay, this does this? So that's what we're going to work on. Now the example that I'm going to use here to discuss this is climate change. And you don't have to have one opinion or another about climate change to get an A grade in this class. It's going to be independent of that. But there are things that I want you to know, among which are the 5 different things that are part of a way you can prove causation. Now these are the 5 that I've boiled it down to for this class. Other instructors or textbooks or websites might have a different set of this list, but it should have some overlap with mine. I want you to know what a longitudinal study is. And I want you to know what a confounding variable is. I also want you to know the difference between climate and weather. So those are a few of the things that you should pick up. Now let me give you kind of a quick list of those 5 things. And I think this should be on one of the slides of your handout, so I'm not going to pause that much as I go through these things. If you have a cause and effect relationship, you should have the correct temporal relationship. The cause comes before the effect. It's kind of a chicken and egg thing. What else? How come this isn't moving? Replication of studies. You should see study after study saying more or less the same thing, that A causes B. So that's something else that you should see. And these aren't just any studies. These are studies that are in refereed journals and places that you can go for well thought out research. Dose response. There should be a dose response in a lot of cases. And we'll see what that is. You should be able to rule out confounding variables. Now we've mentioned a little bit about confounding variables, but we'll take a little bit deeper look here as well. And you should finally be able to explain why the cause creates the effect. What's the mechanism? So, for instance, why does smoking cause lung cancer? Well, because nicotine, an ingredient in cigarettes, binds with radioactive radon in the air. You suck it into your lungs nice and deeply thanks to the menthol that they add. And there, it destroys your DNA, and eventually you get cancerous growth. Nice explanation. All right? You should be able to explain what's going on there. The first stop in our journey here is climate versus weather. So, what's going on here? Weather is what's happening outside right now. Weather changes with the day. Climate changes with your region and with your latitude. All right? Different regions have different climates. You know, you can be in Southern California and have some nice weather right now. My cousin was just coming back from Florida telling me, hey, it's 76 degrees and sunny here. I'm like, yeah, it sucks to be you. We got 4 inches of snow. All right. So we have a little bit different philosophy there. In any case, weather changes with the day. Climate changes with the latitude. Let's start with the correct temporal relationship. I mentioned smoking just a minute ago. You see that nice temporal relationship here with smoking and lung cancer. So if you notice, the blue graph represents cigarette consumption, and the red graph represents death rates due to cancer. And now what's going on here is that there's a little lag between these two, about 15 or 20 years. That's how long it takes for lung cancer to develop. All right? But given that lag, take a look. These kind of march up and down in lockstep, don't they? So you have the cause coming before the effect. Perfect. That's exactly what you want to see. Now with our example, we need to know a couple things in order to examine cause and effect relationship, say, between carbon dioxide and global temperatures. And we've got a lot of really sophisticated, clever ways to know this. We can look at ice cores going back 250,000 or even 800,000 years, and lots of fancy geochemistry can help us determine this stuff. You can look at lake sediments and fossils. You look at the ratio of oxygen 16 and oxygen 18 isotopes. Now this is getting into geochemistry, and I don't want to overwhelm you with that kind of stuff. Suffice it to say that with our technology, we can really, really recreate environments that no human eye has ever seen. But yet we can know temperature, carbon dioxide, and oxygen levels for those ancient environments. So now, what's going on with CO2 and global temperatures? Well, it's not always the nice, clean picture that we saw with smoking and lung cancer. It's a little bit nuanced. That's because the heating of the Earth isn't always uniform. Depending on the tilt of the axis and what ocean's getting warmed up, you don't have the nice, dose, or not dose response, but you don't have the nice cause and effect kind of graph that we had just a minute ago. It's a little muddied here. And part of the reason that is because sometimes you'll get some warming in the southern ocean. That releases some more carbon dioxide, helps warm things in the northern hemisphere, and so on. It's a little bit murky, but it does exist. We do have the nice temporal relationship. We can explain what happens here very, very well. Replication of studies. If you're actually going to have a dose or a nice causal relationship, you should see lots of studies saying the same thing. Now, what amazes me is that there's a perception in the public that there's actually a lot of disagreement amongst people who study this stuff as to whether or not climate change is man-made. And the fancy term that you might hear in association with this is anthropogenic. All right, is that true or not? Well, there's a lot of people that think that, no, yeah, the climatologists, they can't agree on that. In fact, there's a website. They even sent me an email, not an email, but a letter a long time ago asking me to put my name to this. Saying that, we don't believe that climate change is real. And they cite that they have 31,487 Americans think that climate change is not real. And they have degrees in science. Well, yeah, they might have degrees in science. They might even have some PhDs. But let me ask you this. Are you going to ask a plumber to do heart surgery on you? No. You're going to go to the experts, right? And what do the experts say? Well, there was a really misguided attempt to determine what the experts say a few years ago. But what they did was they looked at a bunch of papers, and at the top of the paper they got an abstract that gives you a summary. If the summary didn't explicitly say that climate change is a man-made problem, they said, oh, no. They don't think that climate change is a man-made problem. Basically, they're putting their thumb on the scale. So a more reasoned approach, one that I came across just recently, has a much different number that they get there. Now, before we get there, let me ask you, what percentage of agreement would you want to see amongst climatologists as to whether or not global warming was a man-made problem before you'd say, okay, I think there's good agreement there? What's a good number for you? And keep in mind that only 91% of Americans think that smoking causes lung cancer. I don't know where those other 9% are. In fact, that dipped too. It dipped this century. I don't know why. It was at 92 and it dipped to 91. Wow. Okay, whatever. It's a free country. No problem.
Maybe they work through big tobacco.
Yeah, that's true. But back to the question. What percentage would you want to see, what percentage of agreement would you want to see amongst climatologists that global warming is a real problem that we created before you would kind of say, yeah, okay, yeah, that's pretty good. That's convincing. What would be a convincing number to you? Throw out a number in the chat, or throw out a number here. There's several of you here. There's a bunch of you in the chat. What percentage of agreement would you like to see? 90-ish, 75, 80%. Okay. Anyone here? 85? All right. 50? Okay. All right. That's so at least 99%. And these are the people that study this. And these are some really smart people. Keep in mind that we sent a man to the moon with, a computer that is slower than your phone. In fact, the power that you have in an iPhone 6 could control 120 million Apollo missions to the moon. That's how sophisticated the iPhone is. And so to imagine that we can't really predict what's going on with our atmosphere, as tricky as it is, it's just wrong. Anyways, there's really good agreement there. Problem is, people don't read journals. People read social media. So, okay. Dose response. What's dose response? Dose response means more of the cause gives you more of the effect. One of the first studies that I came across that had a dose response kind of relationship was when we started adding fluoride to water. And what you started seeing as kids got older and grew up with fluoride versus got it when they were, in third grade or sixth grade is a lessening of what? Tooth decay, cavities. Exactly. So here again, here's your smoking versus lung cancer rates, dose response. Looks pretty good. More of the dose, more of the response. Less of the dose, less of the response. Here it is for carbon dioxide and temperature. This is going back a couple 100,000 years. Now we can do this with the courtesy of ice core data. But take a look. Do these things, your blue line is CO2, your red line is global temperature. Do these things seem to march up and down pretty steadily together? What do you think? I think so. Now there's one thing that concerns me. I'm not sure if it concerns you or if you've noticed it or not. Anyone concerned by something about this graph? Yeah, let me be very clear about it. It's right there at that right edge. And that was in 2007. Let's take a look at things now. Here's where it was a couple years ago when I started giving this lecture. And here's where it is now. Wow. All right. You see this up and down pattern because of activity levels in the northern and southern hemisphere. When it's colder out, we're not playing as much, so we don't put as much CO2 in the air. So that's why it kind of goes up and down a little bit. There's a lot that comes at play. Longitudinal studies. This is one of the things I wanted you to know about. A longitudinal study is a study that follows a group over time. So you identify a group, a cohort, and you watch what happens to them over time. One of the earliest ones that, again, I came across was the Framingham Heart Study in Framingham, Massachusetts. They studied these people for decades. In fact, they're on their third generation of studying people in Framingham, Massachusetts, and they learned a ton of information about, what affects the health of your heart. Now, that's a longitudinal study is in comparison to a cross-sectional study. A cross-sectional study just looks at your group of people at one slice of time. It says, okay, what's happening right now? And cross-sectional studies are great for establishing an association. But that's not what we're interested in. We're interested in establishing a causation. And that's where a longitudinal study can really help out. Because in a longitudinal study, you can correct for some things. Now, there's some challenges to longitudinal studies. One is that they're costly, take a lot of time. You got to follow people for years or even decades. You get a loss to follow-up. People drop out. They lose their interest in participating in the study, etc. So It's challenging. It's not easy to do a longitudinal study. But the real benefit is that you can control for changing circumstances and for confounding variables. Want to take just a minute for a little funny side story here? Pfizer was testing a blood pressure medication called sildenafil citrate. And they gave it to a bunch of old men with blood pressure problems. And after a little while, it became clear that their medication wasn't doing a good job of controlling blood pressure. And so they're like, okay, you know what, we're just going to stop the study. It's not working. That's fine. Give us back our medicine. And all these old men said, no. And Pfizer became curious, like, well, why? And I'll kind of let you fill in the details there, but sildenafil citrate is better known as Viagra. So, anyways, the point is, you can be flexible with your longitudinal study. If you realize, oh, we should be measuring blood pressure or checking cholesterol levels or something like that, you can adapt. And the important thing is that what you try and do is you try and keep your two groups equally balanced between potential confounding variables. You don't want all the smokers in one group and all the non-smokers in another group. You want to keep things balanced. You want to protect for these other potential confounding variables. And let's try and understand what a confounding variable is. So let me give you an example of a confounding variable. Looks delicious. It's a bowl of ice cream, right? You collect data on sunburns and ice cream consumption. You find that higher ice cream consumption is associated with a higher probability of sunburn. Does that mean ice cream consumption causes sunburns? Better watch out. You're eating ice cream, you might get a sunburn. No. What's going on is you have a confounding variable here. And in this case, it's temperature. Hot temperatures cause both people to eat more ice cream and spend more time outdoors under the sun, or it's associated with those things. And more time outside is going to result in more sunburns, especially when it's hot out. So that's your confounding variable. Your confounding variable is linked to both of your other variables. It's associated with both of these, but there's a causal association here between your dependent variable and your confounding variable. It's the hot temperatures, it's the sun that causes your sunburns, not the rate of consumption with ice cream. But this is associated with both. To be a confounding variable, you have to have something that's correlated with both the independent variable and the dependent variable, but it has to be causally related to the dependent variable. So, all right. Now, with respect to the Earth and climate change, there's a lot of potential confounding variables. The short story is that we can eliminate them. In fact, if you look at the amount of sunlight received, then that would predict that the Earth should be cooling more than it should be warming, and we're warming. I'm not going to make you an expert with the Milankovitch cycles, but basically one by one we've been able to eliminate all the possible sources of confounding variables. So the last thing is plausible causal mechanism. This one's easy. This is just physics. This is beyond debate. They've known about this stuff since 1859. Wow, I said that right. 1859. That's when John Tyndall did an experiment that showed that gases, including carbon dioxide and water vapor, can also absorb heat. That means when they're in our atmosphere, they can absorb heat. So, long before fake news or anything else, we knew the physics of this. So, wow. We can use observations on other planets and stuff like that to make predictions about temperatures. And these are really good models. They work. And what they show you is what we can see in this demonstration here, and that is CO2 and other greenhouse gases like methane and water vapor prevent sunlight from being reflected back out into space. And so it's like putting a blanket around the Earth. And when you do that, all the solar radiation is trapped in the lower atmosphere and it warms things up. It's just physics. And there's no debate about this. There's none. What people might debate about is, whether this is a man-made effect or not. I argue that it's not a man-made effect. Or I argue that it is a man-made effect. And you can see that a little bit in A Tale of Two Planets. Venus is very much like Earth, except 2 light minutes closer to the sun than we are. But would that explain its severe heat problem? If you take a look at this picture here, what it's demonstrating is the sun and how far you are away at the Earth and how far away you are at Venus. One is not really appreciably closer than the other to the point that you're going to feel much more warmth from the sun. Yeah, the Venus gets a little bit more light, but thank you. So its surface temperature could melt lead. Wow, pretty nasty. But it's not because it's a lot closer, it's because it has a lot more CO2 in its atmosphere. Let's finish it up with a little type 1 and type 2 error review. We're going to assume that global warming is not a man-made problem. That's going to be H naught. HA is global warming is man-made. Now, if H naught is true and you fail to reject it, that's a correct decision. But if H naught is, if H naught is true and you fail to reject, H naught is true and you reject it, then that's a type 1 error. Let's see what a type 1 error would mean in this case. Type 1 error would mean you're saying global warming is a man-made problem and you're doing all these things about it even though it's not a man-made problem. What could be the consequences of a type 1 error? Well, you could have an increased energy bill. Could be a loss of jobs in the fossil fuel sections. Could be inconvenient in some ways. Could pay higher prices for commodities. Okay. What about a type 2 error? Type 2 error would be failing to reject the null hypothesis that global warming is not man-made when it really is. You should be rejecting that hypothesis, but you don't. What are the consequences here? Well, we're seeing it now. Severe weather, more droughts. Last year alone in California, over 10,000 homes were destroyed. $12 billion of damage in California alone due to forest fires. Warmer winters mean the spread of disease, like Zika virus. Reduced agriculture, rising sea levels. In fact, the insurance industry tracks the amount of damage due to catastrophic events. And this year alone in the United States has been 18 events that have cost us more than $1 billion each. And the year's not done. Last year there was 22. It's just getting worse. And you can see that here with looking at a graph that represents the date of the first formation of a tropical storm and the last formation. So here's the first formation of a tropical storm throughout the years. Here's the last date. Now we just did some work on linear regression, so this is very timely. This red line is sloping up. That means the date of the last day of a tropical storm throughout the years is growing later and later into the year. Meanwhile, what's the slope of this red line down here, the date of the first date of a tropical storm? Is that slope going to be positive or negative? Negative. That means the date of the first storm of the season is getting earlier and earlier. And so that gap is getting wider and wider. You're seeing more storms during a longer hurricane season. And if you look at data for a smaller period of time, like this blue graph or this green graph, then some of these predictions are getting really, really bad. All right, take a look at this one. It's saying that the tropical hurricane season is getting much, much earlier, according to this last green graph. So lots of problems there. But let me leave you with one little challenge. And that is, let's see. I guess if the biggest challenge you got to do is make sure you know these 5 different ways to prove causation, know what a longitudinal study is, what a confounding variable is, and know the difference between climate and weather. But here's my challenge to you. Write yourself a little letter to give to your grandchildren. Dear grandchildren, as I write this in 2021, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I examined the evidence and I have decided to blank. Fill in your decision. Hope your world is a good one. Love, whoever. So, all right. Comments or questions? Any thoughts on that? All right. Let's stop this and get you out of here.